Hi, and welcome back to the R Bootcamps. We are in Module 2.2, where we are now talking about the tidyverse, which is a set of packages that are commonly used to wrangle data. So by data wrangling, we mean we take what the tidyverse community likes to call wild-caught data, and we make those data, we tame the data and make it put it in a format, a so-called tidy format, that is amenable to analysis, to any type of analysis downstream. And so that's what we mean by data wrangling, and that's what we're going to talk about in this video, because the tidyverse honestly is one of the most popular packages, and in fact it kind of changes the base R a little bit, so that instead of using base R functions, a lot of people are using tidyverse functions. So it's useful to know, even if you don't use tidyverse all the time, to know that it's there, to know how to use it, and to be able to read code that uses the tidyverse universe. All right. So that's what we're going to do. If you haven't already, please go to the website and load the script, save the script into your working directory so that we can pick up there. All right. And first of all, I just want to thank Christine Albano, who put most of this module together. So thanks, Christine. Here is a schematic of the data science process in general. So we have import, which is basically collecting wild-caught data sets. Then this tidy term, which means we want to put those wild-caught data sets into a format that can be used for analysis. We might transform those data, and transform it meaning making summaries of the data, potentially doing some basic checking and make sure the data meet your basic expectations, and look into any weird outliers or things like that. We can visualize the data, visualize patterns in the data, build models from the data, and communicate our results. But right now we're going to talk about the wrangling step, which is these first three: import data, tidy the data up, and make some summaries of the data, transform. All right, so the core tidyverse. The tidyverse itself consists of a whole bunch of packages, but we're just going to talk about a few of them. So the tidyverse consists of many packages, but we're going to talk about dplyr for data manipulation, tidyr for data tidying, readr, which is basically, it's a substitute for the base R functions, read.csv, those kind of functions that we've talked about, and tibble, which is a reimagining of the data frame structure. So we've talked about the data frame as the essential data storage object in R. Tibble is the base data storage object in the tidyverse version of R. All right, and then magrittr is implementing the pipe operator, so it's just a different way of specifying functions. Now the name magrittr comes from René Magritte, the famous painter, French painter, who made this painting. This is probably the most famous Magritte painting, that you see obviously this old-fashioned pipe, and then you say, this is not a pipe. So this is the inspiration for the magrittr package. All right, that's neither here nor there. There are some other packages that are part of the tidyverse, like ggplot2, which we are going to talk about in the next module, and then some other packages that we're not going to talk about at all in this video. The learning goals for this module is to learn the tidyverse grammar, to learn how to use pipe operators, and basically perform data manipulations using the tidyverse. We're going to, at the end, we're going to look at the luberdate package, which is a fantastic package for managing datetime objects in R. All right, so to install the tidyverse, to install it, you use this. So if you haven't already installed it, remember you only have to install packages once. The tidyverse is actually a set of packages, but You can still use install package and just say tidyverse. When you want to access all the functionality of the tidyverse, you just say library tidyverse, and it's all at your fingertips, and you are now in the tidyverse. So let's look at first the pipe operator, because the pipe operator really does change the way our code looks. So you can kind of interpret the pipe operator as, in English, and then. So every time you see the pipe operator, you can read it in your head as and then do something else. So we can take something like this. So we take the object x. So you can start this phrase that involves the pipe operator with take something and then do something. So take x and then take the log of x and then round the result of that operation so that it has 2 significant digits. All right. Take x, then take its natural logarithm, then round the resulting value to 2 significant figures. It makes complex code a lot easier to read, and we'll go through that in R. In fact, let's go to RStudio right now, and let's load up the module 2.2, and this is the tidyverse module. Let's load the tidyverse up. All right, it gives you some warning messages perhaps, but hopefully it looks something like this, and it actually did work. Let's start with a really simple example. So we're going to set the object x to be 3. We can potentially take the log of x and see that the log of x is 1.09. If we want to round that, we could round the log of x to 2 significant figures, and we get 1.1. All right, so that's the operation we're trying to do. But instead of doing the standard R like this, like we've learned in the earlier modules, we're going to use the tidyverse, and we're going to say, okay, take x and then take the log of x. So let's build up this statement using the pipe operator from mgridr. The pipe operator just says take x and then take the log of that. All right, so there we go. Now we can say take x, take the log of x, or take x, then take the log, and then round that result to 2 significant figures, and we get 1.1. So it's good to kind of get comfortable with the pipe operator because you will see it quite frequently. All right, so that is the pipe operator. Let's look at readr just real quick, because like I said, tidyverse has a bunch of functions that kind of override base R functions. For example, when we read data in, instead of reading data in as a data frame, we read it in as a tibble. And a tibble is just a data frame that has some nice properties that the base R data frame doesn't have, but you can use a tibble just like a data frame in base R. So all the base R features or functions that use data frames, you can also use tibble. You can reference columns in a tibble using the $sign operator, just like a regular data frame, but it does have some nice additional features. So a lot of people like using tibbles instead of data frames. To read in a CSV data set as a tibble, we use the read_CSV function. It looks a lot like the base R function read.csv, but this is different. It's read_CSV, and that way we can read in a CSV file in our working directory like this as a tibble. All right, so let's look at that in RStudio. So we're going to import this data. Before we do that, you should probably get the data set, right? So let's so if you haven't already gotten the data set, go to where it says download an example data set and just load this data set into your working directory, and then go to RStudio and we can read that data in. And when you use the read_CSV function, you'll see that it gives you some information that the base read.csv function doesn't give you, including the type of each of the columns that it read in. So you can kind of check to make sure that the type matches what you expect it to be. Let's look at it. When you Control Enter on a tibble, you'll see that by default it gives you some additional information. First of all, it says this is a tibble, and by default it gives you just the first 10 observations. just like if you use the head function, but you don't have to, because by default a tibble gives you kind of a clean printout of what's in the tibble. You can use head and tail if you want. You can look at the end of the tibble just like you can with a data frame. You can use the summary function and summarize all the columns, so just like a normal data frame. So it basically behaves like a normal data frame, but it has some additional benefits. All right, so that is what a tibble does. So a tibble, if you read in the website, it just has several advantages. It has nicely formatted printing, like we've seen, more useful defaults, and we haven't really seen that so much, but one of the defaults involves, say, reading in character data. It's not going to automatically read in those character data as factor variables. It's kind of smart about the way it reads data in. Faster imports, so if you have a big data file, it can be faster, and if it sees any issues in reading in the data, it'll flag those issues and tell you right after you load the data in. So again, some good reasons to use tibbles. All right. The next thing I want to talk about is the tidyr functionality, which is allowing us to take wild-caught data that are in various formats and make it tidy. What do I mean by tidy? It means each variable has to have its own column, every observation has its own row, and each value has its own cell. So you think that that's pretty commonplace, that is exactly how most Excel data sheets are, where every row is an observation and every column is a variable, but you'll see that that's not always the case when you start downloading real data sets. There's all sorts of formats, and they're not all like this. So this is what a tidy data set should look like. You have all the variables represented as columns, all the observations represented as rows, and all the values in their own cell. So the tidyr package has many functions to help us get data into this format. We can use the pivot longer function to get all values and variables from multiple columns. Say we had each row represents a country, and each column represents the value of something like GDP or something per year. Now, each observation is in multiple columns at this point. We have a 1999 observation, a 2000 observation. What we really want in the tidy data set is to have every observation in its own row. So we have Afghanistan in 1999 is one observation, and here's the number of cases in this case. So we take these values and we put them each in their own row to represent a single observation. It's called, the function in the tidyr is called pivot longer. This is actually a new thing that used to be called gather, but nobody could figure out really what gather meant and what spread meant. It was kind of ambiguous what gather and spread meant. Pivot longer is not ambiguous. It takes a data set with lots of columns and it makes it more rows and it makes it therefore longer. And there's another function called pivot wider, which takes lots of rows and puts them together and makes more columns, and so it makes a wider data set, so it's called pivot wider. We're going to look at both of those. So we can go back and forth from a long data set to a wide data set using these two functions. And we'll go through one use case, but if you want to learn more about pivot longer and pivot wider, you can look at this link. This will give you a lot more detail and goes through some much more complex examples. So if you really want to really get into these, you can. This is a good link to go to. We're kind of doing a whirlwind tour at this point. I just want you to know what the tidyverse is and how it works, but we're not getting into the nitty-gritty here. We can use separate if we have a single column that has multiple pieces of data in it. So in this case, we have a rate, which is like cases per the total population size. So if we want to spread those out into different columns, we can do that using separate. So we'll show you how to do that as well. All right, let's go back into RStudio and use some of these tidyr functions. So we're going to take this climb data, and let's look more carefully at this climb data and see what we have. Now you can see that it is not tidy because we have multiple observations in each row. Let's look a little bit closer at what we have here. This is weather station data, and in the column headers we see the name of the station that the weather data was taken from, and then the name of the weather data that this value represents. So this is maximum temperature in Fahrenheit, minimum temperature in Fahrenheit, precipitation in inches. I assume that's the mean, or maybe total precip. We have the and then we have a different weather station here with the same information. And so we have how many observations for every row? Well, 1, 2, 3, 4, 5, 6, and we want to put those into separate rows to make this a tidy data frame, or tibble. So let's do that. We use the pivot longer function, and we take all the columns that are not date. So we look at the column names here. There's one column date, and then there's all these other columns that we need to put into separate rows. So we're basically going to make a new row for every single one of these column names. So for example, for the date January 1st, we're going to have one row for PK, for station PK, max temperature in Fahrenheit, and we'll have another row for this variable and this variable and this variable. So we're going to basically make a much longer data frame, and we're going to have to specify a new column name that's going to store the names of all these different characteristics that we're going to measure for every single date, essentially. And that column is going to be called climb station, because these column names basically combine the name of the station here, the first before the period is the name of the station, and then the name of the climate variable after the period. So that's what we're going to call this, kind of a temporary variable, because this isn't the be all and end all, but we're going to have to, this is one stage we're going to have to go through to make this a truly tidy data frame. And finally, we'll have another column representing, we're just going to call it value. It's going to basically store whatever the climate variable says it's storing. So, if that row is PK T min F, that value is going to basically represent minimum temperature in Fahrenheit. So let's run this, and we'll see what happens. So we can see that this isn't what we want ultimately. What we want ultimately is to have, you have like date, station, what station did it come from, and then minimum temperature, maximum temperature, that kind of thing. So that would be the tidy, because every observation is its own row. Every observation meaning weather data from this climate station on this date, all right? And then you have a whole bunch of different weather data taken from that climate station at that date. This is not what we have right now yet. So we're not there yet. So look at what we have now. We have date. We have this amalgam variable of both station and climate variable. And then we have this value. So we're not quite there yet. Let's use another of the tidyr functions, and that is separate. So we're going to now take the climb station column, and we're going to separate that into two columns, one column for station and one column for the climate variable. And it's going to know that this is a separator, this period. So it's going to, we don't have to tell it that. It kind of will use common separators, and it's going to separate that column. So let's look at that. So we're going to take, remember with the pipe operator, we're going to take this thing we just made, climb longer, and then we are going to apply the separate function to that, and we're going to separate this column into these new columns. So let's run that and look at it. So now we have two columns, station and climb_var. So now we've we've gone one more step towards what we finally want to do in making a tidy data frame. And so we have date, we have one row for every station and climate variable, but now we've separated out the climate variable from the station. All right. So we have one more step to make this a truly tidy data frame or tibble. So let's look at this next row here and this next command. So what we're going to do now is we're going to take this data frame we just made, climb_var separate, and we're going to apply the pivot wider function. What are we going to do? Well, let's look at the data frame that we have to work with. So what we want is we want to have date, station, and then each climate variable as its own column. So what we want to do is make a wider data frame so that we have a single observation for every date and station. But then we have several climate variables that were recorded at that station. That's just a, just a nice, tidy way to record these data. So what we want to do is we want to take this climate variable, right? This climate variable column, and make each of those different columns. So instead of having 3 rows, one for Tmax F, one for Tmin F, one for the precipitation in inches, we're going to add those as columns. So we'll just have one row for that date and station, and one column representing this, one column representing this, and one column representing this. That's going to widen out our data frame and finally get us to where we want to go. So we're going to use pivot wider, and we're going to take the climate variable column, and we are going to make basically new columns for every one of those climate variables that have the same characteristics, the same date and the same station. We're going to then take the value column, and that will be what we record as the value for each of those new columns that we create. So we're going to take the climate variable column, and we're going to use the value to specify what that column should hold, what values that column should hold. In this case, it's actually called value, so it's nice and simple. And let's run that and see what we've gotten. So now we have date, station, and then the 3 climate variables, which is exactly what we want. That is, every date and station represents a unique observation, and that observation consists of 3 climate variables. And so we've done it. We've gotten to a tidy data frame. Now, let's do the same thing, but we can do it with even more efficiency and using the pipe operator to its full extent. So what we're going to do is make a new data frame that takes the climate data, the original uncleaned climate data that looked like this, and then we're going to pivot longer all the columns that are not date. We're going to name the column names are going to be given a new column that's called the climb_var station, and those values are going to be called a new column called value. Then we're going to separate so that we're going to make that climb_var station column into 2 columns representing station and climate variable, and then we'll pivot wider so that we finally get to the tidy state. And we can just do that all in one command using the pipe operator. So take the climate data, apply pivot longer, then apply the result of that to the separate function, and then take the results of that and apply the pivot wider function, and then you have this thing called tidy climb data. So let's run that, and we can see that we got the same result, and we successfully got a tidy data set. All right, so once we have a tidy data set, then we can use the dplyr package in the tidyverse to perform summary statistics in a very nice, easy way. So dplyr is meant to work with tibbles that are in a tidy format, and once you have it in that format, it can make your life easier in making summary statistics, and you'll see this as you start to explore other people's code quite frequently. And in a lot of R tutorials, they kind of start with this kind of stuff. Even though it's not part of base R, it is becoming so common and popular that this is becoming almost like a part of the R language, essentially. All right, so what we're going to do is we're going to take the tidy climate data. We'll first go through it in words, and then we'll look at the code. So we'll take the tidy climate data, and then we're going to group the data by station. All right, and then we're going to calculate summaries and put those summary statistics in columns with names mean precipitation in inches across all stations, mean temperature in Fahrenheit across all stations, and then we're going to transform to a metric system, not the Fahrenheit, but transform to Celsius, not inches, but transform to centimeters. And that's it. So that's what we're going to do, and we're going to use dplyr to do it. So let's look at what we have here. So we're going to make a new data frame called station mean, which is going to be created by taking the tidy climate data and then grouping by station. So this group by function is a dplyr function that is commonly used. So we're going to group by station, and then we're going to summarize, and this is another dplyr function. We're going to summarize, so across all stations, because we've already grouped by station, we're going to summarize the mean precipitation in inches. We're going to summarize it by taking the mean and removing any NAs. And we'll do the same for Tmax in Fahrenheit and Tmin in Fahrenheit. Once we do that, we're then going to use the mutate function, which makes new columns that are functions of other columns. It's going to transform, or it doesn't have to be a function of other columns. It could just transform an existing column. So it's mutate is just a transforming command that transforms an existing column. All right. So we're going to make a new column called mean precip in millimeters, which transforms the mean precip in inches and multiplies it by 25.4 to make it in millimeters. All right, so I think I said centimeters earlier. We're actually transforming into millimeters. And we'll do the same here. We're going to transform the temperature in Fahrenheit into Celsius using this formula. All right, so we're going to use mutate to basically just transform the numbers into a different units. All right, so let's run this, and we can see what the station mean looks like. Now, obviously, we only have 2 stations. So now that we've summarized by station, we only have 2 rows in this tibble. And we have mean precipitation in inches, which was just computed here, right? And then we have mean temperature and maximum temperature and minimum temperature in Fahrenheit. And we also have the mean temperature and we have mean precip and mean temperature in, or mean max temperature, whatever, in the correct metric units that we wanted. And we obtain those by using mutate. Now there are lots of other useful functions that dplyr gives us, and we're not going to go through that in great detail here. Here's an example. Now I totally encourage you to just get the cheat sheet for dplyr and the tidyverse and tidyr because it will just at your fingertips. Then you'll have a resource that goes through a lot of the most commonly used functions. We're not even going through all of them, so this is just a really brief introduction. So here's a variant, a little more sophisticated thing that we can do. We're going to take the tidy climate data that we made. We're going to group by station just like before. Then we're going to calculate a summary for the numeric data only. All right. So we're going to select all those columns that represent numeric data type and only summarize those. All right. And then we're going to transform the temperature data from Fahrenheit to Celsius, and then we'll transform the precip data from inches to millimeters. So we're going to do the same thing we just did, but we're going to do it in a slightly more sophisticated way. All right. So we're going to take the tidy climate data and then group by station, and then summarize if. So we're going to use a variant of the summarize function. It's called summarize if, that summarizes only functions that meet a specified criteria, and the criteria that it is looking for is numeric. So we're just going to apply the isNumeric function in base R to all the columns and only summarize those columns where that comes out true. So is it numeric? And if it is numeric, it will summarize by the mean, and it'll remove all NAs. Okay, once it does that, it will then mutate at. So we're going to mutate at. That is, we're going to only mutate those columns that meet a specified criteria, and that criterion is, it's going to be these variables. So mutate at will mutate specified set of variables, in this case, the temperature variables, and it will apply this function. All right, and that's a function, a generic function for converting Fahrenheit to Celsius. So we're going to mutate a selected set of variables, and then we're going to mutate another selected set of variables, which actually only includes one variable, and we're going to apply this generic function to that. All right, so that's the exact same thing we did, but it's just in a slightly more sophisticated way. We see that especially if you had a whole group of variables that you want to mutate in the same way, then this would be a much simpler way to write that. So let's run that and see that indeed the result is the same. All right. All right. The last thing I want to go through before ending this module on the tidyverse is to go through a package that is near to dear to my heart, because I use it all the time. It's really the one part of the tidyverse that I use all the time, and that is the luberdate library or package for working with date and time objects in R. And the base R capabilities of working with date and time, it's there, but it's a little hard to use, a little clunky, and luberdate, as the name of the package kind of implies, makes it much easier to work with dates. So let's just look at how luberdate works real quick, because I think it's such a useful package. So we first have to load it. It actually doesn't load as part of the tidyverse. I thought it did, but it doesn't seem to. Now let's read in a date string. So it could be any string that is commonly used to represent a date. Let me make another one just to illustrate the point that this is really flexible. November 1977. All right. I don't know why I picked that date. That has no significance to me. Okay. Date string 2. I'll make 2 date strings. All right. Now, let's convert this into an object that R itself represents as a date. All right. So that R will treat as a datetime object. And to do that in the luberdate package, all we need to do is specify the order of, what information comes first, what information comes next in the date. So in this first date string, the year comes first, then the month, then the day. So we just use year, month, day, or YMD, and put in the date string as an argument, and that will give us a datetime object in R. All right. It'll convert it internally in R to an object that basically is representing a date time. So R knows that when it sees that, it is a date time, which is often useful for performing analyses and visualizations. So let's look at date string 2. So let's, here, and I can run this full line. So now we have an object that is correctly formatted as a datetime object. Let's do the same with datestring2. So now instead of YMD, I'm going to do D for day, month, M for month, and then year for Y. So day, month, year. DMY datestring2. And let's see if we can get a datetime object, and we do. So we see that now we have year, like its internal representation is a datetime object, and this is how R will by default print out a datetime object in this format. But the important thing is that we now have a properly formatted datetime object. We have an object that R represents, and R knows is a datetime object. All right, so let's look at some other formats that lubridate recognizes. So if your datetime information or date information is in this format, that month comes first, then the day, then the year, so MDY, you can convert that to a datetime object. And as you probably know, in data sets that you download, dates are represented in all sorts of different formats. And you have to make sure that R knows what year it is, what month it is, what day it is. And to tell R that in just one line is so brilliant. You can just say, okay, you take this, you can take an entire column of formatted, of text strings that represent date times, just like this, or like this, or like this, or like this, all these different representations. And in one fell swoop, we can just tell R, okay, these are date time objects, and this is how it's ordered. You have the month coming first, then the day, then the year, and it will kind of figure out how to parse it. And so just telling it that the month comes first, then the day, then the year, R will parse that properly and know that that is January 31st in 2017, and it'll know that this is also January 1st in 2017, or any other number of formats that we want. It's almost all the commonly used date formats will be parsed properly by luberdate, which is just awesome. So let's try it. So again, we have, it'll parse that and it'll correctly know that that's 2017, first month, and the 31st day. It'll even do that with numbers or dates that are that have no real formatting. As long as we specify the year, the month, and the day, that's the order, it will correctly parse that, which is pretty awesome. And you can even specify the time zone if you want, so that R knows what time zone we're talking about, and would be able to potentially convert across different time zones. We can use luberdate to make our own date objects by crushing together year, month, and day. Perhaps we have columns in a data frame representing year, month, and day, and we want a date object, or to create a date object from those three pieces of information. We can do that with lubridate's makeDate function. And so we take a year, a month, and a day, and we make a date, and it's now a datetime object, or a date object. I haven't talked about time yet, but luberdate works just as well with time. So if we have a true text string that represents a date and a time, luberdate will be able to read it in. So now we specify that this text string has first the year, then the month and the day, and then we use an underscore to represent that now we're going to start talking about time. And then we have hour, minute, and second, and it'll read that in as a proper date time object. All right. Same thing here. This is a differently formatted text string, and it doesn't have seconds. So we just use MDY underscore HM for hour, minute, and we get the correctly represented date time object. Luberdate also has some convenience functions for representing now, the date time that is currently now, but just passed a second ago. And we can specify now, but specify that I want to know what time it is right now at the UTC, which used to be called Greenwich Mean Time, but is now Universal Time Coordinated, or UTC. and we can get the date just by using today, the today function. These are just convenience functions, and again, like all of this boot camp, don't memorize this, but look at the cheat sheet. All of this stuff should be there. Let's practice parsing dates with luberdate, and then we will be done with this module, and you will have a chance to work on the challenge problems. So let's take this datetime object, let's take this string and convert it to a datetime object using the ymd underscore HMS. And one thing we can do with these datetime objects, once they are datetime objects, is to use these convenience functions that pick out the year or the day or the month for a given datetime object. So we'll take this datetime object and we want to know what year it is. It's 2016. We want to know what month it is. At that datetime object, it is month 7, right? So it is the month of July, and if we want to get the month as the name, we can say label equals true, and that'll actually tell us that it is in fact July. If we want to get the day of the month, we use mday. It's the 8th day of the month. If we want to get the day of the year, we get yday. It's the 190th day of the year. If we want to get the day of the week, we can know that that day, that datetime object represents the 6th day of the week. If we want to label, we can say that that in fact is Friday. All right. We've been doing this with scalar, just an individual text string or an individual datetime object, but of course we can do this with vectors, that is columns in a data frame. So most of the time when we use luberdate, we're not just doing this, applying these functions to a single number, but we're doing it for a whole vector of numbers, that is a whole column of a data frame, or a tibble, as the case may be, if we're in the tidyverse. So let's look at our tidy climate data, and let's actually parse some of this. So before we use the pipe operator and everything, let's just look at the tidy climate data and pull out the date so we can see that that is just a vector of strings, right? We can see that, you know, if I looked at the type of this, it should say character, and it is, so it's a character vector. All right. What if we want to parse it and make it a date object in R? We know that it is the month, day, and year, so let's use the mdy function, and let's convert those all, that whole vector, as one. We convert it all into date time. So now for every row, R knows that this is a date, and it's not just a random text string. It actually represents a date with a year and a month and a day. So we can do that, of course, in using the pipe operator. So let's take the tidy climate data. We're going to overwrite the tidy climate data in this case. We're going to, by taking the tidy climate data and then mutating the date function to apply the mdy function. And so now that column will be represented as date objects rather than as strings. So let's do that. And we get now a new data frame where this new column date is now representing truly a date, and R knows that it is a date. And now we can add new columns. So let's take the tidy climate data and then do the mutate. We're going to make new columns. So we're going to make a year column that takes the luberdate function year and applies it to the date so that it extracts the year, and we're going to extract the month and the day of the month and the day of the year. So we're going to add a bunch of new columns and look at tidy climate data has a bunch of new columns, one for month, one for day, and one for year. If we wanted, now we can summarize by year if we want. So we can take the group by, we're going to group by not only station but also year, and then we're going to summarize the precip by taking the sum of precip and making a new column, or making a column called precip sum. So let's summarize by station and year and calculate the sum of precipitation, and we can do that. So for every station and for every year, we'll get the sum of precipitation. So again, pretty cool what we can do with luberdate and the tidyverse. That is where I will stop. Well, please take the time to go through the challenge problems and let me know if you have any questions. Otherwise, I'll see you in the next module.